Hi, and welcome to this session that's being prepared for the purpose of demonstrating the new ASCE 710 wind forces module in the structural engineering library. It's a very powerful module, and there are quite a few steps to it, so we will take it one step at a time and move slowly through all of the different options that are available to give you the best possible view of what the module is capable of doing. The first thing that I'd point out is that the module was introduced in build 6.12.4.24, so just make sure that you're up to that build if you're looking to calculate wind forces in accordance with ASCE 710. You'll find the module here in the Loads and Forces division, and it's clearly labeled Wind according to ASCE 710, so I'm going to double-click that module. When it comes up, it opens to a general tab that provides an input for a description. So what I might do in this case is say something like new elementary school. And this will echo on our printouts as well. I'll move to the ASCE 710 Wind Force Evaluation tab. And the first thing that I want to point out is that the module has been set up so that there are up to 10 possible calculation tabs or slots that you can use. What we had envisioned here is that it might be possible for there to be multiple project sites that are under consideration for a building, or there might be different framing schemes or different architectural geometries that are being considered at different stages of a project, or for certain projects that are a campus type of development, there might actually be multiple buildings on a given site. So for a few different reasons, we provided the opportunity to store more than just one calculation in a given project file. The next thing that I'd point out is the all-important print checkbox. I'm going to just select that right away and point out that the icon represented by the little graphic printer changes from one that's X'd out to one that is in bold, indicating that this is in fact one of the calculations that will print when I do a project print. And this print functionality was implemented because we recognize the fact that there may be reason to save older calculations as a project develops, but they may not necessarily be the ones that you want to confuse the building official with and include unnecessarily. So you may want to save them, but not necessarily include them in your project calculations. Therefore, you can simply deselect any one of these calculations from the print option. The next thing that I'd point out is that we've provided a description, and this is just a little mnemonic that you can use to try to distinguish from among the various calculations that you may have saved. And so what I might type in here is something like architectural layout number 3, perhaps. Now what we're going to do is just work our way through all of the various tabs that are lined up, and they're set up so that you can just work in sequential order, and you'll hit all of the important stops. So starting with the General tab, we've provided the option here for you to select the risk category that's associated with the particular project. So for our purposes, we'll just assume that we have a risk category 2. The next input is the basic wind speed. And wherever we could, we tried to provide the references to the appropriate figures, tables, diagrams, etc. in ASCE 710. So let's just assume that we have a 125 mile per hour wind. The directionality factor is also something that you can enter, and in this case we actually have a helpful pop-up here that reminds us that for the main wind force resisting system for buildings, the directionality factor should be 0.85. So I'll leave that at 0.85. For our purposes, I'll assume that our exposure category for our building is such that when the north face of the building receives positive external pressure, it qualifies as exposure B. When the south face receives positive external pressure, it actually goes up to an exposure C. When the wind hits the east face of the building, it's exposure B. And when the wind hits the west face of the building, it actually jumps all the way up to exposure D, just for variety. And so we can see this effect in the pressures downstream. I'll assume that our topographic factor is just to be left at 1.0 for all four directions, but just note that you can enter the K1, 2, and 3 values associated with each of the four different directions here, and let the program automatically calculate a KD factor, a KZT factor for you. The next section is the building flexibility selection, and there are three options here. The first option is to assume that the building is rigid in all directions, therefore having a natural frequency that's greater than or equal to 1 cycle per second. The second option is to use the program to calculate the frequency according to the referenced sections of ASCE 710. This is a powerful new section of ASCE 7 that allows us to approximate the building frequency based on the construction type and the building geometry. And you see reference to a frequency tab here, which if we used that second option to calculate the frequency according to ASCE 710, we would then come on to a tab that allows us to identify the building construction type, and it would use the assembled story data to determine an approximate building frequency based on the prescriptive methods that are in ASCE 710. So very powerful tool there for designers. The third option for defining the building flexibility is to just enter the frequency, assuming that it's known perhaps from a three-dimensional model that's already been constructed of the building. And so I'm going to assume for our purposes that we have done just that, and we've already determined that in the north-south direction we have a frequency of 1.1 hertz, and in the east-west direction we have a frequency of 0.9 hertz. And so in the summary box below it tells us that in the north-south direction our building is considered to be rigid, and in the east-west direction the building is considered to be flexible. The last thing that we need to do on the General tab is to provide the horizontal and vertical dimensions that are going to define the overall structure. And so for our example, I'll assume that the horizontal dimension in the north-south direction is 200 feet. I'll assume that the horizontal dimension in the east-west direction remains 100 feet. And I'll assume that the mean roof height of our building is 50 feet. So that completes everything on the General tab. The next thing that we'll do is move to the Story Data tab. And on the Story Data tab, what we need to do is use the Add or Edit or Delete level buttons to create the vertical stacks of floors that are in the building. So what we'll do is click the Add button, and I'll enter a description of first for first floor. And I'll say that the height to this story, and this is always referenced from grade, so this will be a growing number as I move up the building. We'll say the height to the first story is 12 feet. That would be the height to the first structural floor above grade. These last two inputs are somewhat cryptic. They're given to us by ASCE 710 using their nomenclature, E sub Rx and E sub Ry. They're defined as the average distance between the building shear center and the center of mass. There's also a footnote over here that indicates that those values are only needed when the building is determined to be flexible in a particular direction. Understanding that some workflow processes might be to use the built-in flexibility tool to calculate the approximate frequency. And we're only at the Story Data tab now. It's possible that some users may not know whether the building is flexible or not. So I'm just going to populate these with a value, presuming that I've done some calculations and determined these values off to the side. And I'll just show you that it's not going to hurt anything for me to have a value specified in the rigid direction. It's just not going to use the value. So I'll click OK, and there's our first level that's been entered into the table. I'll just work through and populate a few more floors here so we have something interesting to look at. The height to my second floor I'll assume to be 24 feet, so maintaining a 12-foot floor to floor. And then I'll add a third framing level. I'll assume that the height to that floor is 36 feet, so again a 12-foot floor to floor. And then finally I'll add a roof on the building. And I'll assume here that our mechanicals distribute underneath the roof, so we've got a higher floor to floor of 14 feet, bringing the height to story to a total of 50. So there we can see the running total of the H sub I values, the height from grade to each of the floors. Here's the calculated story heights, and then here are the E sub R for X and for Y directions. And at this point, we'll assume that we're done assembling the story data for our particular building. The next tab is the gust factor tab. When you move to the gust factor tab, you're presented with 4 sub-tabs, one for each of the 4 elevations of the building. When I look specifically at the north and the south elevation tabs, we can see that it's echoing the fact that our building is rigid in this particular direction, and it's calculating the gust factor according to ASCE 7 26.9.4, and it's indicating what the value is in the north and in the south direction, or when those elevations receive positive external pressures. The internal values are echoed down here so that you can take a look at what's been pulled out of tables and what's going into these calculations. And I would also point out that you have the option to force the gust factor to be 0.85 in keeping with the ASCE 7 option that allows us to do that. Now, things are a little bit more interesting in this building when I look at the east and west elevations, because in those 2 directions, the building we know is flexible. So here, the program is calculating the gust effect factor in accordance with the reference section for flexible or dynamically sensitive buildings. The only additional piece of information that's required for the calculation of G for flexible buildings is a damping ratio in a particular direction. And so for our purposes, I will just assume that a 2% damping is acceptable for us for both the east and for the west elevations. And now we can see that we have values of the gust effect factor for all 4 elevations. So not very much input required from us when we're here on the gust factor tab. The next tab in line is the enclosure tab. This is the one that's used to determine the enclosure classification of the structure. And the 3 possible options are an open structure, or an enclosed, or a partially enclosed structure. So the first thing that we do is we separate out the math that's required to determine whether or not the building qualifies as an open structure. Note that if you know that your building is an open structure, you do have the option to just indicate that with a selected tab or button, and all of the input goes away as it would no longer be necessary. Let's just assume that we're not clear on whether or not our structure is open. And so we're going to choose the option to specify values and evaluate the conditions. Now what I'm going to do is just populate the values of the gross area for each of the 4 elevations and the area of openings associated with each of the 4 elevations. I have this worked out off to the side. I know that I have 5,000 square feet in my north wall, and I'm going to assume that I have 300 square feet of openings in that particular wall. And in the south elevation, it's also 5,000 square feet, but it's only 20 square feet of openings. In the east wall, the longer wall, it's 10,000 square feet, and I'll assume 20 square feet of openings in the east. I'll also assume 20 square feet of openings in the west wall and finish off with 10,000 square feet for its gross area. And when I accept that value, we see that the building does not categorize itself as an open structure. Once we've determined that the building is not an open structure, then we need to move forward and we need to check each respective direction, assuming that it is the elevation that receives positive external pressure, and we need to determine whether the building is either enclosed or partially enclosed for wind on that particular elevation. The gross area and area of openings in the roof now come into play, so I'll just finish off the data input by indicating that I have a 20,000 square foot roof, and we'll assume that it has 24 square feet of openings. Now what I can do is drop down and take a look at the tabs that refer to each of the different elevations in the building. And for each of these elevations, I have a few different options. I can either choose the option that lets the program run through the calculation to determine whether it's enclosed or partially enclosed according to section 2610 of ASCE 710. Or if I already know something about the building, I can just declare that the building is either enclosed or partially enclosed when this particular elevation receives positive external pressure. So for interest's sake, I'll let the calculations take place. And what I can see is that I've got my calculated values presented here, and then I have my checks for the three different conditions to determine the enclosure situation for each of the elevations, and then the result is indicated down here. So because of my fairly large area of openings that I provided in the north wall, the building qualifies as being partially enclosed when the north wall receives positive external pressure. But if I just click through to the south wall, I can see that the building qualifies as enclosed in that direction, or I should say when the south wall receives positive external pressure. And the same is true when the east and west walls receive positive external pressure. So we have a building that will be partially enclosed when the north wall receives the positive external pressure. And that's all there is on the enclosure tab. So now what we can do is move over to the velocity pressures tab. The velocity pressures tab indicates the values of kH that will be used when each of the following walls experiences leeward or sidewall pressures. And then it also reports the values of QH that will be used when each of these respective walls experiences leeward or sidewall pressures. The table presents the values of QZ for each of the four elevations, as well as the values of KZ that are used to calculate it, and those vary as a function of height from 0 up to the mean roof height that's specified. The next tab is the pressure coefficients tab. This tab starts out by echoing some of the results that come from the enclosure classification that we determined. It tells us that we're going to use the following GCPI values when the named elevation receives positive external pressure. So here we would expect to see this higher value of GCPI when the north wall receives positive external pressure, but notice that the south and the east and the west use the lower value of 0.18 because each of those walls, when each of those walls receives positive external pressure, the building was determined to be enclosed. The next section on this tab is for us to specify the CP values that we need to use, and at this point I would just highlight this button which reproduces many of the figures from ASCE 7 for your reference. And so at this point, what I'll do is come over and start to populate this table. The way that we read this is, what value do we want for the program to use when the north wall receives windward pressure, or is the windward wall? So in all cases, according to ASCE 7, the windward wall always uses a CP value of 0.8. So I can just type those in, 0.8. And then I can come back and just refresh my memory again that side walls always receive a value of 0.7 negative. So I can revise these so that they represent negative 0.7 for the sidewall conditions. The last thing that I need to think about is the fact that my building is long in the north-south direction, 200 feet long and 100 feet wide. So the L over B ratio is 2 in the north-south direction. And that's going to help me with my leeward wall values, because that's going to tell me that in the north-south direction I need to use a CP value of minus 0.3. So minus 0.3 when the north wall or the south wall are leeward walls. And then finally I can revisit that table once more and see that when the L over B values are 0.5 for wind in the east-west direction, I need to use a CP value of negative 0.5. So that helps me to just populate this table. Now I've got all of my wall CP values populated. The next thing that I need to do is I need to take a look at defining CP values for the roof. And again, these figures will be helpful. What I would like to do is just clarify that I'm going to assume that we have a 10-degree sloped roof, so a fairly low sloped roof. And we'll assume that it has a ridge to it that runs in the north-south direction. So what that's going to mean is that we're going to have two different conditions: wind perpendicular to the ridge and wind parallel to the ridge. Now, if my ridge runs north-south, the perpendicular winds will be the ones that hit the east and west elevations. So the way that I might set this up is I might come in and select an option to say that I want to create a wind condition which will be for perpendicular winds, and let's just say that these will be the ones that will be on the windward roof. Now we know that these are going to be the ones that are going to populate values into the east and west directions, and if I come back to our table here, I can see that if I look at the roof pressure coefficients table and I look at the condition for winds normal to the ridge, where the slope is greater than or equal to 10 degrees, I know that I'm going to be reading this portion of the table. I have a mean roof height of 50 feet, and in the direction perpendicular to the ridge, or in other words for wind east-west, I have a 50-foot length. I'm sorry, I have a 100-foot length, so that means that I'll have an H over L of 0.5. So for the windward condition with a roof slope of 10 degrees, I might come into this table and pull out a negative 0.9 value. So these will be my east and west values. 0.9 when the wind is perpendicular, and we're looking at the windward side of the building. And then I need to create a leeward. So let's just borrow that and do a little editing here. And again, I'll jump back over to my table and I'll see that now I'm looking at a condition of a minus 0.5 value here for 10 degrees leeward side with an H over L of 0.5. So minus 0.5. So still working in the east and west cells only, minus 0.5, minus 0.5. Now the next thing that I need to do is I need to think in terms of what happens when I have wind that's parallel to my ridge. So back to my table again. The bottom half of the table handles conditions where you're parallel to the ridge. My mean roof height is 50. The length of the building when the wind is parallel to the ridge is 200 feet. So that's a value, an H over L value of 0.25. So I'll be reading in this category here. And we can see that they haven't made things easy for us. They've actually varied the CP values as a function of the horizontal distance from the windward edge. So what I'm going to do is populate my table with minus 0.9, minus 0.9, minus 0.5, and minus 0.3 for CP values, just to be very thorough and to show you what you can do with the program. I'm actually going to jump over to a spreadsheet where I've typed some of this out already and do a little bit of copying and pasting here and say that we're going to set up an item that is for wind parallel. So we know when we're talking about wind that's parallel, we're going to be working in the north and south cells of this CP table. And to begin with, it'll be a minus 0.9, minus 0.9, north and south. Notice that I'm leaving the cells blank where I don't want a value calculated. And that's an important thing that I shouldn't gloss over here. It says enter 0 or leave a cell blank to skip a calculation in a particular direction. In other words, it wouldn't make any sense for me to try to calculate a windward and leeward perpendicular to the ridge type pressure in the north-south direction, because the north-south direction is not perpendicular, it's instead parallel. So I tell the program that by leaving those blank. The implication there is that in this table there are some conditions where there are extremely small values, generally indicated to be for interpolation purposes only. But if you do happen to have one of these values that's very small, then the footnote goes on to indicate that you're just supposed to enter a very small non-zero value, and then the program will actually calculate a pressure for you in that direction. Okay, so the next thing that we're going to do is create a condition that is for wind that's parallel again, and for a different range, distance from the windward edge, for H over 2 to H. However, ASCE 7 has told us that the values don't change there. It's still 0.9. And then we'll look at a condition that goes from H to 2H. And here they tell us that we're to use minus 0.5, minus 0.5. And finally, we look at a condition that's parallel and greater than 2H from the windward edge. And here our values are minus 0.3, minus 0.3. Now I should point out that these are just representative values that I've chosen for my particular building, for my particular geometry, and that it's essential that the designer be intimately familiar with the ASCE 7 method and with this figure that I keep popping up, or with the appropriate figures for the building that's being studied. I'm just doing something for illustration purposes here so that we can take a look at some results downstream. Okay, at this point I've populated all of the input that there is to populate on the pressure coefficients tab. Now I'll move over to the wind pressures tab, and now we start to look at some results. Notice that there are 4 wall tabs here. So when the following elevations receive positive external wind pressure, I can look through and I can see windward wall pressures for both the positive internal pressure condition as well as for the negative internal pressure condition, again based on the GCPI value that's been determined to be appropriate back in the enclosure classification determination. And then when the north wall receives positive external pressures, I also have windward and leeward walls. The leeward wall would obviously be the south wall, and the appropriate leeward wall pressure would be 22 psf under the positive internal pressure condition, or about 8 psf under the negative internal pressure condition, and so on for the sidewall pressures. And also notice that here is a table of the roof pressures, and notice that while I'm focused on the north wall being the windward wall, all the program reports is the 4 items that I created indicating that they are wind parallel conditions. This is because I only put factors in the north and the south input cells for the parallel condition. And so here are the wind or the roof pressures due to wind under the positive internal pressure condition and under the negative internal pressure condition for the various locations that we set up in that table. And I can click through and I can take a look at these for all 4 of the respective walls being the one that receives positive external wind pressure. Now, pressures are nice, but what we really like to see is forces. So I'll move over to the Story Forces tab, and then to start, I'll just collapse all of the branches so that it's the most compact. And I'd like to just jump straight down to a checkbox here. That's an important one to decide. What this does is it indicates to the program whether we want the bottom half of the lowest story force to be included in the table for us to refer to, or if we want it to be hidden from view, assuming that the wall spans simply from, say, a slab on grade or a top of a foundation wall up to the first structural floor, and the lowest half of the lowest story worth of wind just goes to the ground. So for completeness, I'll select that checkbox so that I can show you those forces in the list. The next thing that I'll point out is that the table comes in pre-populated with 4 load cases, which come from Figure 27.4.8 of ASCE 710, namely Case 1, which uses full wind pressure in one cardinal direction, Case 2, which uses 3/4 of the wind in one cardinal direction and an accompanying torsional moment that's defined here in the figure. Case 3, which can be thought of as quarterly winds, where it uses 3/4 of the pressure on 2 sides, perhaps it's clearer to say on a given corner, and we work our way around and look at each corner being the windward corner. And then finally, Case 4, which uses 3/4 of 3/4, which turns out to be about 0.563 times the pressures on each corner, and an accompanying torsional moment, which is defined here in the figure. So that's the background behind the 4 different cases that you see referenced here. We'll get to the minimum in just a second. So starting with Case 1, if I expand that, I can see that I can take a look at details for the north, south, east, and west walls in turn being the windward wall. And then I can see the data that I've entered for the different levels, ranging from the base level, because I've chosen this option to show the force that's down at the ground level, all the way up to the mean roof height that I've defined. It indicates the vertical ranges over which each of these levels applies. It echoes the tributary height that's a function of those vertical ranges. And then we can see a wind story force that's tributary to each of these levels, which is determined based on the pressure distribution that we've seen back here and the vertical height that's spanned by that particular level. I'd point out that we tried to toe the line with the algebraic sign convention. So for winds on the north wall, those are winds that move in the negative or push in the negative y direction. So that's why we see negative algebraic signs here for wind in the y direction. And likewise, if we look at winds on the south wall, those are winds that push in the positive y direction. So those have positive algebraic signs. I'd also point out at this point that we'll see different values in my example for wind on the north wall versus the south wall, and that relates all the way back to different exposure categories that we picked, B for the north elevation and C for the south elevation, in addition to different gust effect factors and so on. So quite a bit potentially influencing the difference between these pressures that we can see. But I'd point out that case 1 is doing just exactly what we expect it to do, which is the full wind pressures in either the X or in the Y direction for each of the 4 different directions. And notice that there's no torsion being reported, consistent with what we saw for case 1. It's just forces, not torsions. Then, by way of example, if we start to look at case 2, we can see the same type of information, but the force is now ratioed down to 3/4 of the full force. And notice that there is an eccentricity defined, and the force times the eccentricity results in a story torsion that should be considered to be applied in either the clockwise or counterclockwise direction. And if we worked our way through, we would see similar results for the rest of case 2. Looking at case 3, this is the one where we have quarterly winds. So now we can see that we pick up a force in both the negative Y direction and the negative X, because this is wind on the north face and on the east face, so pushing in the 2 negative directions. But again, no torsions indicated in any of the case 3 information. And then moving down to case 4, still quarterly winds, but now we're at the 0.563 level of force in each direction. Notice that there are eccentricities reported. Notice that it's determining the eccentricity as a hard-coded function of the building dimension for the force in the Y direction. Notice that it's some calculated value in the X, or for force in the X direction, and that's because we determined that our building was flexible in the east-west direction, and therefore it's using those E sub R values in a prescriptive formula to calculate the eccentricity to be applied in that direction. Somewhat fictitious, because all the way back at the story data, I just took a guess at a 6-foot dimension, and so that's where those values are coming from. But nonetheless, a difference between the way the moment arm is handled for the rigid direction and for the flexible direction. And then to arrive at the story torsion, it's simply taking the wind shear in the Y direction times the corresponding arm for that direction, and summing that with the wind shear in the X direction times its corresponding arm for that direction. And we would see similar results for all 4 corners, if you will, throughout the case 4 story forces information. Now, this last item in the list is the minimum that's prescribed by ASCE 7. Section 2747 tells us that we can't design the building for less than 16 PSF applied uniformly to the full elevation of the building. And so for convenience, what we've done here is just determined what the area of that elevation is for each direction, and then multiplied that by 16 PSF and reported those as forces. And you're free to use these in any way that you see fit to best suit your design philosophy, and integrate those into and work them with the story forces that you see from the various cases up above. There's some varying interpretations on how exactly to apply that minimum, and so we didn't want to force any decisions there, but we wanted to provide the information since we could calculate it. Now, the last tab that we have is called base shears and torsions. I'd point out that this also includes the checkbox to decide whether or not to include the component of force that would be down at the ground level or tributary to the ground level, so you can alter these values to bring them in concert with what you decided on the story forces tab, whatever your need or your design philosophy is. But these simply look at the same 4 cases plus minimum for wind on each of the different elevations or corners. and it integrates, if you will, the story forces or the pressures over the heights. In other words, it's summing the story forces to come up with a total, what you can consider to be a base shear in a particular direction and a total base moment or base torsion, if you will. Not coming from any particular location specific to ASCE 710, but more provided for informational purposes for folks who have an interest in just trying to compare what are the winds doing to my building as compared to what are the seismic loads doing to my building. And so we thought, since we had it, we would present that in the form of a base shears and base torsions type of table for your information. Now, the last thing that I'd like to point out about the ASCE 710 wind forces module is the fact that there is quite a bit of information, quite a few permutations of the same information worked in multiple ways, and all of this leads to the possibility of voluminous output. And so what we've done here is we've implemented a few print properties from the properties button here that lets you just drill into the specifics of what you do and don't need should you decide to make a print. So here we've made it possible to turn off the detailed wind pressures if for some reason pressures is not really what you're interested in and you're just trying to get to, say, the story forces for the purpose of loading a 3D model. Then you might deselect wind pressures, and perhaps base shears and torsions is interesting but otherwise not essential. And so you might just deselect those and indicate that in addition to echoing all of the input and showing us the enclosure determination and the gust factors and documenting all of that information for submission, what you really want is the detailed story forces, just as an example. So hopefully that's helpful in terms of saving a few trees when you get to the point of printing. So with that, that brings me to the end of the ASCE 710 wind forces module. We hope that it's useful, but as always, we welcome any comments from the user base. If there is anything that we can do to improve this, to make it more useful, to clarify any of it, please, as always, don't hesitate to get in touch with us at support@enercalc.com with those suggestions and thoughts, and we'll definitely give them consideration. Thanks very much for your time, and have a great day.